I'm Lonapi Shaicholat from International School of Engineering, Chulalongkorn University. Our today topics is the design and modeling of a variable stiffness spring mechanism for impedance modulation and physical human-robot interaction. The work have been done when I was a postdoc at MIT Department of Mechanical Engineering, and we have a great contribution from Dr. Satoshi, and we have great support from Dr. Kreb when we are in the 77 lab. And we are going to develop active bodyweight support system. And active bodyweight support system require a high force actuator to carry the human weight. And to have the high force, we need a high transmission ratio. And for high transmission ratio to provide high impedance to prevent falling, the intrinsic property of the actuator cannot allow us to have the high backdriability. So there are two complementary strategies to moderate the mechanical impedance of actuator. The first way is from the feedback control, and the second way is from the adjustable intrinsic properties of actuator. Satoshi proposed the impedance control for the high force actuator. As you can see, we can control the motion of the linear actuator by just a potato by force at the point. For adjustable intrinsic property, in the second video is what we are going to focus by today, is the variable stiffness spring mechanism. When we adjust the position of the roller support, we can adjust the stiffness at the endpoint, the interaction between the human and the robot at the endpoint. And the last one, in the third video, we have the macro mini actuation concept. And we use the ER fluid brake. And when we change the voltage applied on the ER fluid, it can control the friction in the brake. And sometimes we can completely connect the endpoint to the high force actuator. And sometimes we can control the endpoint by the mini motor with low impedance. And for today's concept, the small deflection leaf spring mechanism. If you see in the schematic, we have the stiffness modulation module that moves to the left and to the right to adjust the unsupported length of the spring, which affect the stiffness at the endpoint. And we also have the equilibrium position adjuster that move vertically. The equilibrium position adjuster adjusts the equilibrium at the endpoint. In the same time, another role is to maintain the small deflection at the endpoint, so that we still use the stiffness model to relate the endpoint force by the measure deflection at the endpoint. The stiffness model, the basic one shown here, the stiffness K is related to the unsupported length L by the modulus of elasticity E and the second moment of area. But can we apply this model to our prototype that show on the left? Our prototype, the stiffness adjuster, use dual roller pair slider. It means we have offset between the first and the second pairs of roller. And what's gonna happen if the spring has some deflection slope between the roller? So when we zoom in to our hardware prototype here, the main component is a leaf spring that have one fixed end and another end is connected to the human. And we have the linear encoder to measure the deflection at the endpoint. And when we apply the force will transfer from the leaf spring to the roller and to the bearing support. So with this design, it consumes very low energy to maintain the stiffness, because the motor, the rolls of the motor, when the motor rotates, it drives the ball screw and move the roller to the left and to the right, but the motor don't need to carry the interaction force. The interaction force is transferred to the bearing. The motor is just need to modulate the stiffness and maintain the stiffness. So if you see, we have the roller slider with dual roller pair slider. The schematic show the dual roller pair slider. If we have the deflection slope between the pairs of roller. The roller offsets now shown by L0, and the deflected length Lx is the distance from the last pair of roller to the applied force position. From the general linear Euler-Bernoulli beam equation, we have the fourth order differential equation that relates the deflection, vertical deflection, y, to the loading function. The loading function, we have the RA, the reaction force on the left pair of roller. We have RB, the reaction force on the right pair of roller, and the endpoint applied force P. And the reaction force, of course, we can obtain the magnitude of the force by the equilibrium of moment. And we know that the dual roller pair slider at the roller's position, we can constrain the vertical displacement. So the displacement at y at x equal to 0, y0 is 0. And also the displacement when x equal to L0 on the right pair roller is also equal to 0. We have one important assumption. If we see in the schematic, we can see the blue line. The blue line comes from, we assume no bending moment in the left segment. It means that no bending moments mean the slope on the left segment gonna be constant. When we have constant slope, it means the second and the third derivative of the displacement gonna be 0. By solving this differential equation, we have the deflection model that relates the vertical deflection y by the position, the horizontal position x. And if you see in the plot, we have the blue plot that comes from our proposed model, and the red plot comes from the basic model with the ideal cantilever support. For the ideal cantilever support, you can see the 0 slope from the left pair roller when x 0, and the right pair roller when x equal to 27, we have 0 slope. And we just see the deflection in the deflected length between the right pair roller and the applied force position. But for our proposed model, we allow to have the non-zero slope at the contact point between the rollers and the spring. So by here, we can see that maybe the real stiffness of the spring may be lower than the theoretical stiffness obtained by the ideal cantilever support. So how about the stiffness? The stiffness at the endpoint position is the ratio of the applied force by the vertical displacement at the endpoint position. So we rearrange the equation and we obtain the stiffness as a function of the deflected length. What is the deflected length? The deflected length here is shown by Lx, and x is the position, x equal to L0 plus Lx at the position of the applied force position, and we also measure the vertical displacement at that position also. So how can we use the stiffness model as a function of the deflected length? We use this relationship to select the spring for our prototype. To select the spring, we may begin from the schematic shown here. The schematic shows the stiffness adjuster, and the stiffness adjuster can move to the right-hand side closer to the applied force position. If the stiffness adjuster moves to the right-hand side, it's gonna change the L0 from the L0 of minimum stiffness to the L0 of maximum stiffness. Because if we move the stiffness adjuster to the right-hand side, we increase the stiffness, right? So the traveling distance, the maximum traveling range of the stiffness adjuster need to be the difference between L0 min and L0 for the maximum stiffness. On the contrary, it can be the difference between the L1 min and L1 max when L1 is the deflected length of the spring. So how can we obtain this traveling distance? From the previous derived model, we plot the stiffness varying against the deflected length L1 with different thickness of the spring. from 0.02 inch thickness to 0.042 inch thickness. And the horizontal line showing the desired minimum stiffness and maximum stiffness. The intersection between the curve of the spring and the horizontal line show the deflected length that we require by the spring to generate that stiffness. So minimum traveling length, if you see here, maybe the red one with the low thickness spring, we may get the shortest traveling distance, but we cannot select the red one because if we select the red one, the point that we can have the maximum stiffness is the deflected length will less than 1.2 centimeter, which means it's less than the radius of the roller, and we cannot make a real prototype. So in this case, we select the spring with the thickness of 0.028 inch for our prototype, and the traveling distance of the stiffness adjuster gonna be, it needs to be moved from the deflected length of 1.6 centimeter to 8.9 centimeter, only about maybe 7 centimeter of the range. And we develop the prototype and characterize the prototype. Here is the foresight static experiment. We fix the position of the stiffness adjuster and we vary the deflection and measure the force, and we can have the linear relationship between the force and the deflection when we fix the position of the stiffness adjuster. The slope of this plot gonna be the stiffness of the spring at that deflected length that relate to the stiffness adjuster's position. So when we plot the stiffness varying against the deflected length, here the stiffness is plotted in the log scale, and we have two different thickness of the spring, 0.028 and 0.062 inch. And we have the experimental data and plot with the basic model with the ideal cantilever support. And our proposed model, considering the non-zero slope, we can see that at the extreme deflection at high stiffness region, our proposed model can provide better estimation than the basic model that shown by the dashed line. So yeah, we also show the control of the stiffness modulation for the full range of stiffness modulation. The stiffness adjuster moves from the minimum stiffness position to maximum stiffness position, and we measure the force, and we also measure the endpoint deflection. And we can see here, for the force, we can see the overshoot during the forward motion. And we fix the endpoint deflection, but the data that we read by the linear encoder is not constant because it has the effect of the deflection slope in the spring. So this is one concern when we need to estimate the endpoint force by the low-cost optical linear encoder. The couple effect of the displacement and the deflection slope is appear in the encoder data. And here, the stiffness modulation for the full range take less than 0.25 seconds. And to sum up, we propose the stiffness model considering the non-zero slope between the roller support position, and it can provide better estimation than the basic model assuming ideal cantilever support. And we have the guideline for the selection of the spring thickness so that we can have the shortest traveling distance of the stiffness adjuster, which means we can have the fast stiffness modulation and have the compact size actuator. And we have the ready to control hardware system. The vertical position mover move up and down, and human perform interaction with the robot by apply the interaction force at the endpoint, and the stiffness modulator try to change the stiffness to maintain the small deflection. So that's all. Thank you very much.